Greetings and salutations, magical chemists. Let's talk about Le Chatelier's principle in a little more detail. First things first, it is important to note that a shift to the left or the right does not actually say anything about the overall rate of the reaction. It only tells you about the relative rates of the forward reaction with respect to the reverse reaction. For example, if you have this generic exothermic reaction where heat is a product, well, if the temperature of the system goes up, equilibrium would shift to the left to use up some of the added heat. However, this does not mean the overall rate will be slower. It does mean a new equilibrium position will be reached, which has more A and B and less C. And in fact, hopefully you remember from kinetics, increasing temperature will always increase the rate of the reaction, which means increasing temperature will cause equilibrium to be reached more quickly, regardless of the direction of shift. Okay, next we're going to talk about how equilibrium systems can be represented graphically. There are two very common graphs that you need to be able to interpret. The first one is when you're graphing the rate of both the forward reaction and the reverse reaction versus time. The idea is if you're looking at the rates versus time, by definition, equilibrium will be reached once forward and reverse rates are equal. However, another type of graph we use commonly shows the concentration of reactants and products versus time. And it's important to recognize that equilibrium will be reached when they are not necessarily the same concentration, but they are a constant concentration. Oops, small typo in the notes down there. Sorry about that. You can actually identify if you have a reactant or a product-favored reaction just by looking at the concentration versus time graph. In a reactant-favored reaction, at equilibrium, the concentration of reactants will be higher than those of products. And if it's product-favored, well, it'll be the other way around. Okay, so let's see what happens to these graphs if we stress the system, Le Chatelier style. So there's a couple of different things you can do, and therefore there are a couple of different graph changes that you need to be able to recognize. The first, and possibly most common, is change in concentration. You will recognize a change in concentration graph when you're looking at a concentration versus time graph because there's going to be a quick spike, either up or down, if something was added or removed. And then, because that of course causes the equilibrium position to shift, there will be a slow change in the concentration of whatever's left over. Or whatever wasn't changed in the first place. Of course, when equilibrium is reestablished, that means that the concentrations will be constant again. Now let's see what could happen in a rate versus time graph, because you have to be able to identify this kind of change in both graph types. Well, if you notice, the thing that we added over here, the carbon monoxide, is a reactant. If you dump in a bunch of reactant, now there's a higher concentration of reactant particles, greater probability of a more effective collision. So you'll notice that the forward rate, because it was a reactant, spiked upward. Then, as more products are made, you'll notice the rate of the reverse reaction slowly increases until the rates are equal again. I was trying to help you predict which direction or how to identify when you would spike forward versus spike reverse, and I realized that these statements were going to be accurate if you add the increase concentration, but not if you decrease concentration. So we're going to rewrite these. Basically, the reaction rate's going to spike up if you increase the concentration of something, and it'll spike down if you decrease the concentration. You have to consider your knowledge of Le Chatelier and if a reactant or a product concentration is being changed to determine if the forward or reverse reaction rate will spike up or spike down. You can also show a change in temperature over time and basically use Le Chatelier's principle to figure out if you have an endothermic or exothermic reaction. The way you're going to recognize that it is a change in temperature and not a concentration change, when you look at the concentration versus time graph, all of the changes are slow. There's no spike. And the concentrations are going to shift until they all become constant again and equilibrium is reestablished. Now, it depends on if it is an endo or exothermic reaction and if the temperature went up or went down to figure out what's basically going to increase or decrease. you can see a temperature change on a rate graph as well. Although this one, honestly, it pretty much looks about the same as decreasing the concentration of something, because in the rate versus time graph, it's still a sudden spike in one of the directions. So in this case, you have a spike down in one of the rates and then a slow change in the other rate. Okay, this is another one that we're going to edit, because if you increase the temperature, remember that means the rate of reaction is going to go up, and it's the rate in both directions. If you decrease the temperature, the rate is going to go down. So you can predict from the direction of the spike if the temperature was increased or decreased. You have to use your knowledge of Le Chatelier and endo or exothermic reactions to figure out, well, which rate would spike up if I increase the temperature, and vice versa. Of course, equilibrium will be reestablished when both rates are once again equal. Notice in this case, they're equal again at a lower rate because it was at a lower temperature. Okay, one last graph to consider. What happens if you add a catalyst? Well, remember that adding a catalyst doesn't actually change the position of equilibrium, but it does mean that you will reach equilibrium faster. So that is what's shown in the concentration versus time graph. For the catalyzed reaction, you'll notice that the concentrations level off sooner than they do for the uncatalyzed. It's because it reached equilibrium faster. For the rate versus time graph, this is the only time you will see both forward and backward reaction rates changing at exactly the same amount at the same time. Zoom! They both hop up by the same amount. Just a quick reminder before we segue away from these delicious graphs. Nothing can ever completely undo the stress on the system. So shifts predicted by Le Chatelier's principle will only partially counteract the stress. Graphically, I think that's easiest to see if we go back to the change in concentration graph. If you remember, this is where we were at equilibrium and then we dumped in some extra carbon monoxide. Well, notice, Le Chatelier says, gotta use up some of that extra carbon monoxide to get back to equilibrium. But when equilibrium is reestablished, you do still have a smaller amount more of carbon monoxide. So we couldn't completely undo the addition of carbon monoxide, but we mostly did. Okay, let's change gears and talk about how to answer free response questions about Le Chatelier. There is a pretty straightforward pattern that you can use, and if you follow this step-by-step pattern, you will always make sure that you hit the key information needed to get full credit for your free response answer. The first thing is just to make sure that you have identified whatever stress or change has been made. And then you're going to figure out, okay, well, what will that stress do? Basically, will it cause it to shift right, shift left, or no shift at all? And you can say shift towards reactants, shift towards products, that's the same difference. But basically, identify the stress and then figure out what shift will happen. Then, since it's free response, well, if it says explain, which it usually does for these, you get to explain why the change you identified would cause the shift you identified. And remember, it's always framed in this idea, well, it's going to counteract that stress to reestablish equilibrium. And of course, the last step is just to make sure your explanation actually answers the question that they asked. So let's take a look at some examples. In example number 1, we're looking at a temperature change. Notice that they specifically told you, oops, that's not a highlighter, that they specifically told you it is an exothermic reaction. And 25 to 50 degrees, they're saying the temperature went up. And the question specifically wants to know, well, what is the effect on the equilibrium constant K? So first, I'm just going to identify what happened. Well, I increased the temperature. And you have to specify for a temperature change if the reaction is endo or exothermic, because that determines the direction of shift. You might be thinking, well, they said it in the question, of course it's exothermic. But the reason that you include it is for you to show that you know that it matters. Because if you were answering a question about changing concentration and they told you it's exothermic, it wouldn't matter. That's why it's so important. Now, in this case, because it's exothermic and heat is a product, it turns out increasing the temperature will cause the system to shift left to use up the added heat. So that's where we're connecting in. The leftward shift will undo the change by using up some of the added heat. And that part of that sentence has basically already done steps 1 through 3, but we still need to answer the question. So this is where we get to talk about, okay, well, if it shifted to the left, that's increasing the concentration of reactants and decreasing products to reestablish equilibrium, yada, yada. But remember it said K. What about K? Well, that will decrease K. And now we have answered the question. For the second example, now we're given a specific reaction this time around, and they said, hey, we're going to add some more stuff, some more of your gaseous A, which is a reactant. And we want to know, what effect will that have on the concentration of B? Intriguing. Well, we're just going to follow our steps. First, we identify what happened, and then we figure out what way that's going to make it shift. Well, if you add more Ag, it turns out that is totally going to increase the concentration of A, so the system will have to shift right to use up some of that A. But now we have to answer the question. Well, if you're using up A, you're shifting and making more C, B gets used up too, which means the concentration of B will decrease. Not too bad. All right, we are going to try one more example, and we are going to make a small edit to this example problem, and then we're going to try one on our own. Okay, for this third example, we're going to use the same reaction system that we just looked at, but we're going to change B to solid. Because this time around, we're going to remove some B from the reaction container. And you might be thinking, why does it matter if B was a gas or a solid, right? If you remove it, it's still going to shift to replace it. Well, no. Remember, solids are not included in the equilibrium constant expression. So they won't actually, if you remove B, but there's still enough B left for the reaction to happen, it's not going to have any effect. Kind of crazy. That is a very classic trick AP question. So watch out for that. Remember to consider the state of matter when you are answering equilibrium problems. All right, so here is one for you to try on your own, and then we can go ahead and check. It says, in the following reaction at chemical equilibrium, what is the effect on the reaction mixture if the volume of the reaction container is decreased? And, of course, explain. So go ahead and try this, and when you're ready to check your answer, unpause the video. Okay. First things first, we're talking about volume, which basically changing the volume changes the pressure, right? So you have to consider number of gas particles on both the reactant side and the product side. Well, there are 2 gas particles on the reactant side, one N2 and another O2. And hey, look at that. There are 2 gas particles on the product side. Well, you know what's interesting about this? That means decreasing the volume of the container has no effect because the reaction has an equal number of gaseous reactants and gaseous products. If you decrease the volume, you have less space, so you would shift towards fewer gas particles, but it's the same on both sides. Okay, there are 2 more free response problems for you to try. Let's take a look. You should absolutely, definitely, and positively try these on your own, because I am just going to pop up the entire answer after you have tried them. All right, so take a moment, try these on your own, pause the video, and when you are ready to check, you know what to do. Unpause the video. Okay, we are increasing the temperature of an endothermic reaction, which basically is the equivalent of adding in some reactants. You might think this was another trick question because calcium carbonate is a solid. So you're like, oh, it's not going to have any effect on it, right? Well, the concentration's not going to change because it has a constant concentration. However, if you are shifting right, that means you have calcium carbonate breaking apart to form your products. And therefore, you will actually decrease the amount of calcium carbonate, even though its concentration will remain the same. All right, let's check the last one. If you haven't tried it yet, now's your last chance. Whoosh. Okay. Well, this one was one of those trick questions, but they're very common, so I thought we should practice it again. When you add more KCl, KCl is solid, so it does not affect your equilibrium position, solids aren't included in the equilibrium constant expression, yada yada, so there is no effect on the reaction mixture. So there you go. Thank you for playing with Le Chatelier, and, of course, the glories of chemistry.